I hope everyone's doing well today. I am Mr. Ish. Thank you for joining me for this video. In this video, we're looking at an area calculation related to a hyperbola. It would be more technically appropriate to do something like this than calculate an area of a hyperbola. Hyperbolas are usually open face and they have two different curve orientations. When you're doing an area calculation related to a hyperbola, it's a more appropriate term in terms of the endeavor we are pursuing. A horizontally oriented hyperbola, standard orientation around the origin, that's the equation. This is the area I'm examining right over here. Perhaps the most common exercise, and that's what we will do over here. You would need to get an equation over here, and you can by solving for y from right over there. You can do a common denominator, x squared b squared minus y squared a squared is equal to a squared b squared. Anything related to a hyperbola with regards to area calculation is long, it's tedious, and it's sometimes difficult. Solve for y. Minus y squared a squared is equal to a squared b squared minus x squared b squared. Flip everything around. You have y squared a squared is equal to now x squared b squared minus a squared b squared. Here we can actually solve for y. We'll have a x squared b squared minus a squared b squared over a squared and root. You can isolate a b squared from the numerator, but you can bring out a common root, which is b over a, and we'll have x squared minus a squared. You can see b squared got isolated here, a squared on the bottom, bring it out as that, and that's equal to y. But when we're looking at this representation, this being equal to y, we're looking at the area of this, because the radical makes you lose a lower negative outputs. You end up just looking at this. Obviously, then you have to multiply it by 2. What is our integral limits? Well, I'm looking here from a vertex to a focal point. You could essentially draw any vertical line and do a calculation up to that vertical line, but for consistency's sake and using a specific point, I'm looking at from a vertex to a focal point. What's the area of a hyperbola on one side to a focal point? That's what I'll do. What will be my integral? It will be from a up to c times 2 to capture this. We don't need to worry about that side, we're only looking at one side. And right over here, b over a x squared minus a squared dx. That's my integral, which will give me a template. Since here we're looking at everything conceptually, you can see there's no numbers over here. I don't have numbers here in the denominator. Since we are looking at everything conceptually, we will have a template develop. Then we can apply that template to an example. Integrating this will be the most tedious aspect of this entire video, but we will do it. We have a x squared minus a squared form. We're going to do trigonometric substitution. X here is equal to a secant theta. Dx is equal to a secant theta tan theta d theta. Theta 1 and theta 2. Everything with regards to this and the limits. You're doing an arc secant of a 1, which will be a 0, and you know you're doing that arc secant of a over a. Upper limit, it'll be arc secant of, you're bringing c in place of x, c over a. That's what it will be. Look at my limits, and look at this, 2b over a. My lower limit is a 0, my upper limit is arc secant c over a. We'll bring in the substitutions. In place of x, I'm writing a secant theta will be a squared secant squared theta minus a squared dx, you know, was a secant theta tan theta d theta. Look right over here. You'll isolate a squared, you'll have a secant squared theta minus 1. This thing right here is equal to tan squared theta. You'll have a squared tan squared theta all within a radical, and this right here is equal to a tan theta. A tan theta will multiply with all of that. You'll have a squared secant theta tan squared theta. We'll bring that into play. The a squared will get pushed outside. I have a 2b a squared over a. My limit 0 arc secant c over a. I had here a secant theta tan squared theta d theta. If it was the reverse, secant squared theta tan theta, I could have done u substitution, but I can't do it anymore because this spoils it for me. What can I do over here? I can substitute a trigonometric identity in place of tan squared theta, which is what I will do. Simplify this, 2ba, that's what I have, or I'll write 2ab. 0 arc secant c over a. We'll have here a secant theta times, well, tan squared theta is equal to secant squared theta minus 1 d theta. Separate everything across that minus sign, and I'm going to do it for you right over here. We'll end up having secant cube theta minus secant theta d theta. Understand what has happened over here. This thing right here, you know there's an identity tan square plus 1 is equal to secant square. Tan square is equal to secant square minus 1. This secant square minus 1 got substituted for tan square theta, Secant square theta minus 1 will distribute across that minus sign with this. You'll have a secant cube theta minus secant theta. That's exactly what comes about, and we have to deal with it. It's prudent now to separate everything across the minus sign because a reducing formula has to come over here. You'll do 2ab 0 arc secant c over a. I'm just trying to save space by writing it that way. I have a secant cube theta d theta minus this 2ab 0 arc secant c over a secant theta d theta. There will be an excellent shortcut that will come in a little bit of time, and I'll talk to you about it when it comes. Open this up. Secant reduction formula n minus 2, n minus 1, where n here is equal to 3. We have an integral secant n minus 2 theta d theta plus secant n minus 2 theta tan theta divided by n minus 1. Bring that in right over here, particularly for this part right here. We will have a 2ab secant theta d theta in an integral secant theta d theta plus this secant theta tan theta over 2. There's an over 2 coming here. 1 divided by 2, 1 over 2 minus that part right over there. What's the antiderivative of secant theta? Well, it's a natural log. Natural log secant theta plus tan theta. I have to do this. It will be an AB natural log secant theta plus tan theta. I am distributing the AB across its terms as well. Plus AB secant theta tan theta minus what you see over there, 2AB natural log secant theta plus tan theta. Now you know we have limits over here involved. I'm just temporarily cutting them out. Why am I cutting them out? Because it's the same limits applying to an expression that has been expanded and separated. There's no u substitution, there's no change in those limits. Those limits will come back. I'm just expanding and simplifying for right now. This right here is a common term with this. This right here is my positive term. I can write the positive term first. AB secant theta tan theta minus positive AB minus 2AB, it'll be a minus AB natural log secant theta plus tan theta. And now if we want, we can bring our limits. We have an arc secant c over a, and then we have a 0. We have to compute all of this. When we compute all of this, we'll get our template expression, which will enable us to calculate the area of that representation I showed you at the very beginning. In all instances, theta is coming from here. Theta is equal to arc secant of some expression right here. That some expression represents a certain angle theta, which will then enable us to determine a right triangle. We don't need to see this anymore. What is our triangle? It's this right here, theta. Let's look at this upper limit, c over a. With regards to the secant, it's always hypotenuse over adjacent, c over a. If you want to find this side, obviously it's going to be c square minus a square. But think about how everything has come here from a hyperbola. In a hyperbola, when you have the a, the b, and the c, the vertex, the focal point, and the minor point, the relationship between these three items is this: a square plus b square is always equal to c square. If I'm looking at solving for b, it's equal to c square minus a square and a root. I'm having here a c square minus a square and a root. Rather than continuing forward with that, I can replace all of this with a b, because that's exactly what it's equal to with regards to hyperbola. I have a b, and a c, and that will greatly simplify everything. Just remember what I've done over here. The relationship in a hyperbola between a, b, and a c, vertex, focal point, and a minor axis. Endpoint b is always equal to square root c square minus a square, which is exactly what I had over here, and I've substituted it. Now what we need to do is, using those items from that triangle, we'll fill in the theta angles. I have a AB. What's secant of that theta? It's a c over a. What's tan of theta? It's a b over a. Now you'll see it greatly simplify everything by means of this little shortcut we've taken. AB natural log. What's secant of theta? Well, it's c over a. What's tan of theta? B over a. Now all we have to do is consolidate. We can, because there are things which will cancel out here, and there's things which can simplify here. My entire template, when I simplify it, I'm going to bring it for you right over here. We don't need to see this anymore. Look right over here. I have a b square c a divided by a square, and that's going to be equal to b square c over a. All of this expression is going to give me b square c over a minus. Now look right here. I have a common denominator, a, c, and a b on top. It'll be ab natural log c plus b over a. This right here will be the expression or the template that will give me the area of that hyperbolic representation I showed you earlier. Now let's make all of this meaningful by representing a example and utilizing that. Our example is this. I have a 4x squared minus 9y squared equals 36. It's a hyperbola. I divide everything here by 36 because I want to convert it into the standard form. I'll have an x squared over 9 minus y squared over 4 equals 1. This expression right here is representing x squared over a squared minus y squared over b squared is equal to 1. A here must be 3, b must be 2. The roots of these items you see. C here will be obviously, you know, a squared plus b squared is equal to c squared. The relationship in a hyperbola, it's different than the relationship in an ellipse. Anyhow, 9 plus 4 will be root 13. What are we looking at right here? We have a vertex 3, 0 and a minus 3, 0. It would look something like this. Obviously you have asymptotes, but we don't even need to look at asymptotes. Our minor axis endpoint will be right here, 1 will be right here, but we're looking at this part right here and nothing is drawn to scale. This is my focal point, here's my vertex. I'm looking at the area of this portion right here because everything was derived from a representation from here. A lower limit was a vertex and an upper limit was a focal point. Now if I want to determine the area of this, I have the formula and the format for you. I have the values. B squared C will be a 4 root 13 divided by A, which is a 3, minus AB 6 natural log C plus B root 13 plus 2 all over A. You compute that and you'll get your value, and we'll end the video with this computation. We'll do the natural log component first. Square root 13 plus 2 divided by 3 natural log times 6. Now we'll do the left hand portion. 4 times square root of 13 divided by 3 minus that saved value from the natural log aspect, and my end result is 1.0565. You can say unit square, but I won't put any units. 1.0565. That would represent the area of this, and it already includes the times 2 to capture this lower part because my integral already included that. This template is the result of that integral procedure. And that's it. Area related to hyperbola, particularly the most common application or the exercise you would see would be something like this. Have a good day. Bye.